Yeah, there are a ton of applications here, so we're just going to touch on a couple. And these are from your text as well. So one thing I want to note is we do have a really important base that we often use with exponentials, and that is the natural base e. So there's an irrational number e that has many, many applications. It's kind of like the same idea as pi, which you're probably familiar with. E is defined as the value of 1 plus 1 over n to the nth power as n goes to infinity. So as n gets larger and larger and larger, e is that value that it's approaching. So what happens here is as n gets larger and larger and larger, the approximate number that you're approaching is this one right here. It is irrational, so it does keep going on forever and ever and ever. There's no pattern to your decimal, so I have just listed the first 9 decimal places. But this here is your e value. Very similar to how we have that pi is about 3.14, right? So it's another irrational number that occurs very often in nature. And in the world around us. So it's a common base. We call it the natural base. So your function looks like this, and it's called the natural exponential function. So one model that we can use with it is on the gray wolf population. So the reputation for the gray wolf acquired in the United States in the 19th and early 20th centuries was not a good one. They called it, I guess, the insatiable killer. Although the label was undeserved, an estimated 2 million wolves were shot, trapped, or poisoned during that early time. And by 1960, the population was reduced to only 800 wolves. So the figures here show the rebounding population in 2 recovery areas after the gray wolf was declared an endangered species and received federal protection. So here you have the northern Rocky Mountains, and here you have the western Great Lake regions. The exponential function given right here models the gray wolf population of the western Great Lakes X years after 1978. So our data there starts in 1978 and continues through 2018. Now I don't have data for every year here, but we do have it for 5 different years during that time period. So we're focusing on the western Great Lakes here. According to the model, what was the gray wolf population ran into the nearest whole of the western Great Lakes in 2018. Now, again, we're looking at the model here, which means the equation or the function. Now, X is years after 1978. So I'm looking at 2018 minus 1978. And I see that 40 years have passed during this time. So we're going to plug in X equals 40. Now, for something like this, I encourage you to take your time and perform the order of operations. So the first thing I'm going to do is I'm going to clean up this exponent because we always work inside things. Now, there's no parentheses, but we're inside the exponent. So that sort of counts in the same realm of trying to clean that piece up. So I'm going to do 0.0325 times 40 first. So I get that this is 1,144 e to the 1.3 power. Now that comes out even, so I'm using I would use all my exponents. I'm sorry, all my decimal places there. And then next I would do my exponent. So when I type in e to the 1.3 power, let me show you this on my calculator. So here I'm using that TI-83 calculator. I do have an E key right here. Mine's in yellow. So to use the yellow piece, I just hit the second button first and then hit that key. And you can see it gives me e to some power, and I can type in 1.3 and hit enter. So I get 3.66929. I'm going to continue this 6668. So I'm going to use all those decimal places, and then I'm going to multiply it by that 1144 and hit enter. And I get 4197.675388. So with exponentials, they do increase or decrease very, very quickly. So it really is important to use as many decimal places as you can. A lot of students get rounding errors because they don't use enough decimal places and then they get the answer wrong. So as you're doing your computations, use all the decimal places you can and then just round at the very end. So here we are rounding to the nearest whole. So this rounds to about 4,198 wolves, right? That 7 will bump up because of the 6. And this is part A here. Now, if you do not have an E on your calculator, then what you would do is I would use this right here to represent E. Some texts will have you round it a little bit more, like your text recommends using 2.72. I don't think that's enough decimal places. Personally, I think you should use a lot more decimal places. So if you don't have an E feature on your calculator, I would use this and go out, the 9 decimal places as you're using it. So you would just use that for your base instead. Does this model under or overestimate the grade of population? So in 2013, the actual population, according to the data, was 4,222, right? Just looking at that table. So actually, this is really, really close. Again, it's not perfect, but it is really close. So our model is a little bit shy, right? So we're what, 24 wolves shy. This is a little bit low. So our model underestimates the data by, and then you take the 4,222 minus 4,198, and you get 24 wolves. So our model does underestimate a little bit, but overall, I think it does a really good job here. So that's pretty close. And I want to do another application here with exponentials. And this is going to be a business or a money one. And this is compound interest. So compound interest is the interest computed on your original investment as well as on any accumulated interest. So for instance, if you leave your money in the bank, let's say in a savings account, and let's say you don't touch it, maybe you have $500 in there. Well, typically at the end of the month, the bank will pay you interest. So they may say, hey, you earned $2 interest this month, and they'll put that $2 in your account. So what happens is now in month 2, you don't just have $500, but you have $500 plus your $2 interest. So you have $502. Now, when they compute it the next time, you're starting with $502. So you get a little bit more interest the next month. Maybe you get $2.05 instead. So now that goes in. So your compound interest is when you take that interest at the end of the month and you put it back into your account. So your account value is growing, and then it keeps happening over and over and over again. So that is compound interest. It also works for loans too. So it goes both ways. It works for savings accounts, and it also works for loans and things like that. Now in the formula, P is your principal. That is usually the sum of money that you have in the account. R is your annual percentage rate in decimal form. So how much interest rate that you're earning. And then here in our first example, we're just going to do the interest calculation once per year. So your base formula looks like this. You have your original principal, and then you add in your principal times your rate. And this right here gives you that interest, which we usually call I. And then what happens is you add that in the end of the month, and then now the next time you do it, you have a different starting value. So the next time you do it, you're starting with this as your new principal. You're still multiplying it by that 1 plus R though, because you're going to take your interest again. And at the end of month 2, you end up having a square factor there because you're taking the interest on the account, which already has interest in it. And then at the end of month 3, the same thing happens. So each month that account is growing little by little. So when you get interest, you're getting more and more and more because your savings account is going up. So what happens is this 1 plus R keeps getting multiplied again each month. So what happens is after so many, or here we're doing years. Sorry, it's not months. Here we're doing years. So after so many years, then what happens is however many times you do this, you end up with that factor of T in your exponent. So if you do it T times, let's say T is 5, then you'd have that to the 5th power. So it's however many times you end up doing this. Now, compound interest is actually a little bit more complicated than this. We often don't just compute interest only once a year. Oftentimes we do it monthly or maybe daily even, etc. So there are different kinds of compounding periods. So if you hear annual compounding, that means that interest is calculated only once a year, so every 1 year. If you have semi-annual compounding, semi usually means twice. So you're doing it every 6 months. You're doing that calculation twice per year, which is every 6 months. If you have quarterly compounding, well, think about quarters. That would be 4 times a year. And if we have 12 months, 12 divided by 4 is 3. So every 3 months, you would be computing the interest calculation. If you have monthly compounding, you would be doing this every month, so 12 times a year. And you can even have daily compounding. So at the end of every business day, interest gets calculated and added back into your account. So you're doing this 365 days a year. So what happens is we actually have a finalized formula for compound interest. So it's this one right here. You don't want to use this one. This one is only if it's annual compounding. This one will take into any kind of compounding. So N is your compounding, and then you have your different N values based on what kind you have. T is your years here, and P is still your principal, and R is still your interest rate. And we're going to do some examples so you can see this as well. I will note too that this is some of them. There are some banks that do daily compounding with an N of 360 instead. This is very an old method, because before we had computers, it was very difficult to do these calculations, right? You're using calculators or doing them by hand. So a lot of times banks would round and say that there were only 30 days in every month, which is 360 days a year. So it just makes the calculation easier. There are some institutions that still use that more antiquated system of 360 days. You don't have to worry about that here. I just want to make it known that, when we hear daily, it's typically 365, but there may still be some institutions that are using an older strategy there, older method. Now you also have what's called continuous compounding. So now that we have computers, particularly, right, really we can compound interest continuously over and over and over again in fractions of a second. So instead of waiting to the end of the day to do it, the computer sort of just keeps continuously compounding this interest and adding it back into your account. Now what happens is it's very, very small with each compounding, so you're not noticing it. You're going to see the calculation for continuous and daily tend to be very close, but there actually is continuous compounding as well. And when this happens, when that N goes off to infinity, this part here becomes E. So this is your formula if you have continuous compounding. And then A is your ending balance, so the amount that would be in the account at the end. So let me show you how this works, and I think it'll make a little bit more sense. So let's say you're deciding to invest $8,000. That's your principal. For 6 years, that's your T. And you have a choice between 2 accounts. So the first account, let's see, our principal is still 8,000. Our T is still 6 years. Okay. Now our first account pays an interest rate of 1.2%. And when you talk about your rate, you do want it in decimal form. So to do that, you're going to move the decimal point 2 spots left. And you can fill in any holes with 0. So I'm going to use 0.012 in my calculation. And it's going to be compounded monthly. So if we're talking about monthly here, then our N value is going to be 12. So the second option still has a principal of 8,000. It still has a time of 6 years, but the rate is different. It's going to be 1.19%. So in decimal form, I move 2 spots to the left, 0.0119. And then we're doing continuous compounding here. So on this side, I'm using the regular formula. And I'm going to plug in my values. So my P is 8,000. My R is 0.012. My N is 12. N is 12. T is 6. So T is always in terms of years here in this formula. And then what you need to do is just very carefully start performing the order of operations. So I always work inside. So I'm going to do this division first. So let's see, I get 0.012 divided by 12. So that becomes 1 plus 0.001. And then 12 times 6 is 72. I'm going to add these together. And now I'm ready to start using my exponents. So I'm cleaning things up first. You just need to go nice and slow here. So I'm going to do this part next. And I'm using my calculator. And I get 1.074616683. And then I'm going to multiply that by 8,000. And what I get here is 8596.933, etc. Because it's money, I'm going to round to 2 decimal places. So I have about $8,596.93 for my first account. So if I start with 8,000 at the end of the 6 years, I actually have almost $8,600 in that account, assuming that I haven't touched it. So I'm not taking money out, I'm not adding money to it. So I'm just kind of like leaving it alone. Then you would have almost an extra $600 added in at the end of those 6 years. If we're talking about continuous compounding, then we're using this formula instead. So I have A equals to 8,000 E to the 0.0119 times 6. So this becomes E to the 0.0714. I'm using all my decimal places. With exponentials, it's really easy to get rounding errors. So you want to use lots of decimals. And then I'm going to type E to the 0.0714. So again, I'm just using my calculator here to do those pieces for me. And let's see, I have 1.07. 401.0744, and then I multiply that by 8,000. And I have 8,592.0859. And it's money here, so I'm rounding to just 2 decimal places. So about $8,592.09. Now those values are really, really close. Right here, I have $96. Here I have $92. So in this case, this is a better option for us. So again, if we're investing the money, we want to make more money. So it kind of depends on who's doing the investing, right? If it's us, we want to make more money. So the better option here is option 1. But you really do have to check. So here, our numbers were so close, right? Our rates were really, really close. This one has 12 compoundings a year. This one was continuous. Now, typically, the more compoundings you have, the more money you make overall. But that assumes that everything else is equal. So here, because that rate is just slightly less, even though you're compounding more, it kind of evened itself out. And actually, the first option ended up being the better deal by about $4, $5. So you do have to check, right? So if everything is the same rate, same time, same money, then typically the more compounding, the better, the more money you make. But once you start changing the rates and things, then you kind of don't know what's going to happen. You have to use the formula to figure out what would be the better deal. So this is a really common application with exponentials here. And you see you have a regular exponential problem, and then you also have that natural exponential as well being incorporated.